Et c'est un talk invité que j'ai donné il y a un mois, à peu près. C'est URSI is a Union of Radio Scientists. La plupart du temps, il y a beaucoup d'ingénieurs qui s'occupent d'antennes, de radio wave propagation, satellites that have to do with GPS in particular. So what I had done with this group, you can recognize Kevin as Yang. Haley Song is a graduate student, a PhD student, and PD Chandra is another prof in the department, and he's an experimentalist. He's an experimentalist that has been building and setting up GPS receivers, ionosongs, HF radars in the auroral and in the polar cap region. So most of the instruments, most of the data that we have are from either the polar cap or the auroral region. And it's been, in fact, I'll tell you a story, because sometimes people think that things happen overnight with a switch of, you just turn on a switch and a program is set up. The program that we have right now in space science at UNB is a program that basically we built over the time of about 20 years, 20 to 25 years. So I went to UNB as a recruit, as a faculty recruit to support the Canadian Space Agency Center for Space Research. They had invited a senior guy from Stanford, who had come with a rocket program. He had a rocket program, and the idea was the Canadian Space Agency wanted to set in the eastern part of Canada a center for space research. So they had a senior guy, they hired somebody from Stanford who was working on a detector on Soho and had brought a rocket for calibration that he would have flown for calibration for Soho at that time. So he came, and then the contract was to hire 2 junior faculty, an experimentalist and a theorist. I was the theorist I was hired. So the experimentalist, by the time we identified somebody who now works at the Air Force in California, another brilliant guy who had worked on a rocket program at Berkeley, they were supposed to come and we were supposed to set up the program. It turned out that the senior guy from Stanford was not the right recruit. So he stayed until 1997 and then basically broke his contract and left. So I had a choice. I said, I either stay there or move somewhere else. And the city was a small city, and I had 2 kids at the time, 3 kids at the time. I had 3 kids. I said, I'm not going to raise my kids in a big city. There's no way I would raise my kids in a big city. So I stayed in the place. I stayed, and I convinced the administration to rebuild the program. So the first recruit was Jayachandra. So I brought him in under one condition, that he brings an instrument with him. An instrument, a space instrument of any kind, whether it's on ground or space, put on a satellite or not. Bring an instrument, I will push your appointment in the physics department. And we did. So he brought an ionosong. He brought an ionosong that was being sold all over the world at that time. He came in 2002, 2003. So about 20 years ago. So we started with the ionosong, and in the Department of Geomatics and Geodesy and Geomatics, there was another senior guy who's senior right now, and most of the occultation measurements that are done on quite a few satellites over the last 20 years, he built them in the engineering department at UNB. The Geomatics and Geodesy program at UNB is probably one of the top 10 geodesy and geomatics programs, or at least was one of the top 10 programs. In fact, when there was a Swiss flight 111 that crashed taken off from Boston going to Switzerland and crashed just off the coast of Nova Scotia, the people who basically went after the plane, and it was very deep, was the geomatics people at UNB. And when the Americans realized that we had a group of that stature, they hired all of them and they moved them to New Hampshire. So the University of New Hampshire has now what we would have had on ocean mapping at the University of New Brunswick. And they had to rebuild. So one of them stayed, Richard Langley. If you look at the IEEE journal and look at Richard Langley, he writes a lot of short articles, making things that look extremely difficult from an instrumentation point of view. He makes them very accessible to graduate students. He's been teaching for a very long time. So I said, we're going to build it like that. So we hired the third person in 2007 or 2008 who was interested in the neutral atmosphere. So there's a component in the physics department at UNB, so I'm selling the program in a way. You see, some people from the CRAAG should do the same thing elsewhere. So maybe if I get to know the CRAAG enough, I will be able to sell the CRAAG to other people. So in 2007, we hired somebody who was interested in neutral atmosphere. So he's interested in airborne measurement, wind measurements, very interesting. So we wanted to have a coverage from basically the ground all the way to about 1,000 kilometers. We couldn't compete with the programs that had magnetospheric research or even solar terrestrial interaction at a higher level because you need a satellite program. And in Canada, there's only one place that had one or two places, academic places. There are institutions, research institutions that fly satellites, but on an academic basis, there are only two places that have built satellites, and those who are familiar with SWARM, right? One of the satellites on the SWARM constellation is a Canadian satellite. It's Cassiopeia, and Cassiopeia was first called the EPOC. It's an outflow that basically the satellite was to put instruments to measure the outflow of ions out of the ionosphere. So that's how the programs was set up. We started hiring students, and now we're on the map. So anybody who does scintillation will cite one of the papers that are coming out of our group, no matter where you go. And if you start going into the scintillation program in the Aurora and Polar Cap, there's no way you can get away without citing or taking our data. From the data has to be taken from UNB, so you have to cite the fact that there is a program that looks after it. So it took about 20 years to set up the program. And right now we're thinking, since I'm getting to the age of retirement, I'm going to negotiate the transaction with the university so that I can stay for a little longer time and make it and facilitate the transition for a younger person to come in to continue to do theory. I told them explicitly that if they want to hire another space physicist, it has to be a theorist. Because if we take theory away, there won't be any modelers or anybody who suggests new things to measure or new things to do and so on, and people will become engineers. They will drift towards doing the engineering. So, and we have a couple of engineers in at UNB who have built a new ionosome, completely from scratch. We have spent about almost $3 million just to try and build an instrument that is multitask instrument. Not just, it would not measure just it's not just an ionosome. It had other factors built in it, and we have a prototype. It works, and some people have already expressed interest in getting these ionosomes, and we are replacing all the ionosomes that belong on the Canadian soil by the new ionosome that we're just setting up. So we have few students. We have currently, we have about, between myself, Jay, between the two of us, we have about maybe 12 graduate students. Of the 12, maybe 8 are doing masters, transiting towards PhDs, and 4 are doing PhDs. And we've built also a component that is numerical. And I told you about the thesis that was recently published, not recently, but recently defended by the student. And so that's how you grow organically. So, and it doesn't take too many people, it takes the right people. It's not the number that is important, it's the quality of the people, the intention of the people to do genuine science, and then to invest in graduate students. So we do invest a lot in graduate students. Every graduate student costs us, on average, at a PhD level, costs us about $30,000 so per year. So I said 4 PhDs, that's 120,000. At the master's level, we pay up to 25, so add another 250,000. So we're talking about $500,000 spent on students per year. That's what we do. So if I write grants, I write grants to support graduate students. If my colleague writes grants, he writes grants to build instruments, and the overhead that we get from the instrument is invested in students. Because we know without students we cannot function. We could function, but slowly, very slowly. We're interested in one problem, I'll solve one problem. But if I have 10 ideas and I bring 5 students, I can exploit the 10 ideas. So that's how we've been operating. So what I'm going to do today, I'm going to give you, yesterday I talked globally about what we do with GPS, or at least till the end. Today I'm going to show you the part that I'm most interested in. And that part is basically modeling. See, data, students come to me, we ask questions, we have a regular meeting every Monday, and we start at 10:30 and usually we go until about 1 o'clock. So we have about 2 hours and a half, where all the students come in and we talk about what they've done during the week, and we move on. And if they have difficulties, we resolve the difficulties as we go along. And it's every Monday, and every Monday there's a talk. So somebody from the group will give a talk for 30 minutes to 45 minutes, and the rest of the time is a discussion. So the last 6 months, we had presentations on the ionosome because we were testing the prototypes. The prototypes were giving us ionograms, and we needed to understand whether the ionograms were clearly reliable or not. And it turned out that they are spick and span, as they say. They're pretty, they have high resolution, they're functioning under very strange conditions and so on. So it works. It works, and we're happy because there's data. And if there's data, there are challenges. And if there are challenges, then you can challenge the students, you can challenge yourself, you can challenge, and you can go back and the ones who funded the process of building the ionosome or any other instrument, you tell them, here, it works, and we're going to do this and that and that and that. They're happy to give you more money. More, not too much more, but they give you money so that you can sustain the research program. So let's see what I'm going to do. for those of you who work with radio signals, the first thing is to look at the phase in the signal and the amplitude. So you get a signal, it scintillates, it scintillates. Think of scintillation. There's a song in English that every parent knows when their kids are growing up. They say, "Twinkle, twinkle, little star. Twinkle, twinkle, little star." The stars scintillate. Why do they scintillate? Because they send the light gets diffracted, and what you see is some diffraction pattern at the level of your eyes. So think of that when I'm talking about scintillation. So there's a certain amount of intensity of light that reaches your eye, and there's a phase to that wave that you need to try and decipher, to try and understand. So the next thing I would do, before I go here, I never show data, which is quite interesting. And if I'm showing data, you must question. Those who know me, you will make that joke all the time. So you said, Abdelhaq is showing data. So I'm going to talk, it's not going to the next thing is, I'm going to talk about, there's a signal in the data, and we see what is known as two power laws. So if you have a time series, right, and you take a Fourier transform, and you look at the intensity at each component, and you plot that intensity versus frequency, there's a behavior. So, and if there is a behavior, if you have a log-log plot, you're going to have a power law. A power law means the function is a function of the variable to a certain power. So if you have f of x equals x to the power p, log of f is p log x. So if I plot log f versus log x, I get a straight line. And the slope is p. So that's a power law, because the function is a polynomial of power p, and I need to know what power p is. So I'm going to look at a theoretical model, and I'm going to focus on the wave propagation model. I'm going to focus on what does the wave see as it propagates through the ionosphere. And then I will focus on exactly how to explain the power laws with another tool from statistical mechanics. So those of you who have gone through a physics degree, who've done some statistical mechanics, this is the time to go back to statistical mechanics, the probabilistic approach to physics. So let's start. Here's the data. We're going to look at the amplitude of the radio wave that is coming in, and as the GPS receiver receives it, and we're going to look at the phase. So we're going to take a chunk of the data, the red part here. You can integrate all, you can look at all the data, but we're going to look only at the events where you have large fluctuations.
Sorry, look at after the seismological.
Oh yeah, definitely. In fact, those who do seismology, I can write the equation. I'll show you that they're exactly similar to what I'm going to be writing. Because you're going to solve a wave equation for sound waves. They're called sound waves. So you're going to solve wave equations. So if you have a turbulent system, and your rocks have different densities, different chemical configurations, and so on, you're gonna do exactly what I'm doing. So in fact, I'll tell you, those of you who are in seismology, one of my best friends for a very long time was Mahrez. So Muawiyah was a very close friend, because I did my postdoc at Cornell, and he and his wife were very receptive when we moved with 2 kids to Refeka. So we got to know him. So I learned a lot of geophysics with Muawiyah. In fact, I have in my office. Allah yarhamu, he just passed away, and he passed away 2 or 3 years ago.
2 years.
Yeah, something like that. He gave me, the last time I visited, I was on sabbatical. I went to Cornell for my sabbatical for a short period of time. And he was excited and so on. So he came and he said, Abdelhaq, come to my office. I went down and he had printed for me a map of Idrisi. Do you know the map of Idrisi? Idrisi, the one that is inverted, where Africa is in the north and Europe is in the south. He had a color poster for me, and it sits on top of my desk in my office in Mahrez. So I learned a great deal of seismology from Mahrez. So and you know, he showed me. He used to take me to his office, and he would tell me, "You see these clips?" You know, and he said, "Well, these are clips that we have just recorded in San Diego or something like that." And he said, This is what the difference between S and P waves and so on. So I learned all that nomenclature from him. So they look exactly the same. So we're going to analyze this chunk of data here and here for the same time. And here is what we have decided is the noise in the signal. So what I'm going to do, or what Kaylee Song, the graduate student, did, is she basically calculated the power spectra for these signals. And I have, so if you look at the power spectra, the left panel here is the amplitude spectrum. So this is the amplitude spectrum. It has a very shallow slope here, and a slope, a power law. Remember, it's log plot. So when you fit a line, the slope of the line tells you what the power law is. And this is for the phase. And the phase shows 2 power laws. And the noise is in yellow here. So we know that the part of the signal shows 2 power laws. Yes?
J'ai une question.
Please.
Le slide précédent, qu'est-ce que tu appelles la phase?
C'est la phase, comme si tu disais, it's as if you said, I have a signal, and the signal can be written as A, amplitude, e to the I times the phase. And you can, for GPS, for those of you who know about GPS, what we calculate with the GPS is basically a distance and delays, right? And some delays are due to the fact that you have a phase difference, a phase is changing, and some are due to ionospheric effects, to neutral atmosphere effects.
L'amplitude de la phase, elles sont données par l'instrument.
Yeah. In fact, the GPS gives you the total electron content, and you can relate it to the phase direction. I haven't gone, I should have had a slide about how you, for GPS, when you have, it operates at 2, 3 frequencies now, but at the 2 frequencies, you can have the delays at 1 frequency, delays at the 2nd frequency, and you can play around with the 2.
Just another
Please.
We are familiar with this first, with the power spectrum density.
Yeah.
When we compute it in seismology, we can calculate the length of the fault, the fault, the moment, seismic moment.
Yeah.
Many
Yeah.
about
You're gonna see that. You're gonna see
And
that.
when you have the plateau, it's very short, that's big, it's earthquake, it's bigger.
Right. I'm going to show you that.
It's really
I'm going to show you that formally and analytically, where it comes from. So, yes, you do.
In the previous slide, you showed the
Previous slide.
how did you decide that it is beautiful?
Because there is a background. You know when you don't have signals, right? When there's no signal, no scintillation, you know, your signal is going to be noisy, right? Some of the noise is due to instrumentation, some of the noise is due to the background. So we take it away. So we identify it. And in fact, you could do more. You could do more. Because noise could be white noise, could be colored noise, right? And if it's colored, you gotta ask what makes it colored, right? And the best way to do is to evaluate a probability distribution function of the fluctuations. So you compute the probability distribution, and then the probability distribution, if it's a Gaussian, you know it's going to be white noise. Or if the probability distribution has a tail, then you know is going to behave differently at different frequencies. So we do that. We store all of that when we look at these again. So this is the second event, similar event, but second event with large amplitude fluctuations and phase fluctuations. So this is forward, this is backwards. This is the second event, and you can see again, you know, large amplitudes. The noise is identified as being at this level, and for the phase, the associated fluctuations with the amplitude are here, and the noise in the phase is in here. The solid line is the satellite elevation. So where you are, where the satellite is, with respect, will tell you what the elevation, because it's very important to know where the satellite is. So we plot that information. So
Why you don't use it on
we can. We use both. We use both. I'm a theorist, so I'm just showing you what I like to show you. If the experimentalists were here, they will show you L1, L2, they will show you L3, they will show you, instead of 1 power spectrum, they will show you 10 power spectra, and then they will convince you that there's a pattern, and then they will wave their hands, and they tell you to solve the problem. That is questionable. We can talk about it. So, the power spectra, again, that's the amplitude, that's the wave, and that's the phase. And you can see for both events, you can see the power laws. A power law in the amplitude, the single one, 2 in the phase. I'm going backwards. So, we've established that the data shows some power laws when we look at the spectrum. Now I have to explain that. So I'm going to use a wave propagation model. As they say, hold on to your seats, fasten your seat belts, because we have a little bit of theory. It's not very complicated theory, I can assure you, because it's wave equations and solutions to wave equations. So if I look, this delta E is the component of the electric field. We're looking at electromagnetic waves. So we have an electromagnetic wave propagating. It's not a pressure wave. It could be a pressure wave because the electric field can oscillate. And if it pushes back and forth the electrons, you're changing the pressure, the local pressure, so you can generate a pressure wave. But we're not interested in that at this point. Now, what I have here is the dielectric function. And the dielectric function, the square root of dielectric function is directly related to the index of refraction. Right? Straightforward. We're not doing magic here. Straightforward. The wave propagates at c over square root of epsilon. Right? C over n. That's the phase velocity. So, what I'm going to do, you take this equation, the top equation, and you Fourier transform delta E. So I'm going to take the Fourier transform, so you could look, this is d omega, and I'm going to write delta E in terms of a Fourier transform in frequency space. and I'm going to call it psi. Take this delta, you put it in the wave equation. If you put it in the wave equation, you get this equation. So it's the original equation, you just substitute the Fourier transform, and you get an equation for psi. So, that epsilon minus 1 that appears here, right? That epsilon minus 1 is the index of refraction squared minus 1. And if you're familiar with dispersion relations, this is just, if you look here, what is 4 pi e squared n over n? Can anybody tell me what that is? 4 pi e squared times the electron density divided by n. Anybody a plasma physicist?
Sorry. Plasma frequency.
That's the plasma frequency. So this is minus omega plasma frequency squared over omega squared. And very often, if omega is equal to omega p, you get one limit for propagation. If omega is less than omega p, you can see whether this term is less than, in absolute value, less than 1 or greater than 1. So that's, this epsilon minus 1 here holds, that's the density. That means that's your ionosphere. The ionosphere is hidden here. Right? That's the electron density. So I'm going to play around, put this epsilon minus 1 into the previous equation, and I write an equation like this. This Re is basically the classical electron radius. What it reminds me, it's pretty small, it's 10 to the minus 15. It reminds me that the wave is scattering off electrons. And I have to know what the electrons are doing, because the wave is coming and shaking the electrons. So I'm going to do something else with this equation, because, you know, if you're a physicist, you've been forced to take quantum mechanics as part of your curriculum. So the first approximation that we do, we neglect this term, the second derivative, this second derivative. Now, why do I neglect it? The answer was in the next slide, but I'm sure no one read the next slide. Because there are too many sentences. The students, how many students? The younger fellows. The younger fellows. I see quite a few faces. The younger fellows. Huh?
It's, the flux is not, there are no flux or something.
What does the second derivative represent?
The variation of the flux.
There's no flux. The psi here is the amplitude of the wave. The amplitude, the whole amplitude, the complex amplitude of the wave. First derivative is the slope. Second derivative is
Inflection. Inflection point.
non-inflection,
The
curvature.
Curvature.
And d to x dt squared. Je veux dire la cinématique. When la trajectoire curves this way, the acceleration. And la trajectoire does this way, deceleration. So the second derivative is a curvature. So you have a wave. We assume that the wave is coming down. And then it says, well, my wave amplitude has a curvature. That means the wave is going to be reflected. Right? It goes back up. That term tells me, this term tells me that the waves are going to come back up. But I'm not interested in the waves coming back up, because I'm not measuring things at the satellite level. I'm measuring things at the receiver level. So this term is not going to be important. This term is not, it's a reflective part. If I were interested in the signal coming back towards the satellite, and I had a way to measure it, I would keep this term. So I'm not going to keep it. And this is known in optics as it's quasi-optics or the parabolic approximation. Parabola, right, is usually curvature up. So the curvature, so you neglect the curvature in the z direction. So we're going to take that term away. So my equation now becomes like this. Imagining deep side dz, 2k, RE over 2k, and psi. This is the Schrodinger equation. Deep side dz, deep side dt. H bar is what brings quantum mechanics. Grad squared, RE over 2k, v, psi, psi. So if I consider z to be time, I have the Schrodinger equation. So the space physicists are not usually, they take one quantum mechanics and they stop. If you do theory, they push you with more quantum mechanics. So I'm going to use the tools of quantum mechanics to get. So the first thing in quantum mechanics is the total probability is equal to 1. So in quantum mechanics, this integral of psi squared is just 1. The integral of all probabilities, if you integrate, if you sum all possibilities, you should find the particles. So it's 1. And then it's independent of z, it's an invariant. It doesn't change whether z is equal to 10 or 20 or, so it's the same as dx and psi of x equals 0. And then I could use Parseval's theorem and turn this into an integral in frequency space, or in so I'm going to have the amplitude. I'm going to have information about the amplitude that is hidden in the equation. The second thing is I have an energy-like equation. It's an energy-like. Remember that when you write the Schrodinger equation, A deep C dt is the commutator of H with so the Hamiltonian. So this is the Hamiltonian for my waves, and the potential is the electron density of the atmosphere. So, and this is not an invariant because n depends on z. So dt dz is related to dn dz. Now, those who work with scintillation, most of the time, you're using models, you are using models of thin screening approximation. That means you assume that the ionosphere is a very thin screen. So the variation of m over that, the variation of the electron density over that thin screen is negligible. So if you assume that this is negligible, then T is an invariant. Yeah, so now I have two invariants. Now guess what? How many slopes did I have in the phase spectrum? 2. And I'm going to link that, the two invariants, to the two slopes. So that's, if you got that, we can stop. You got that? So two invariants. Two invariants. No matter what the wave is propagating, these two quantities should not change. Right? So the signal should keep that information. The signal at the bottom of the signal recorded by my receiver should remember that the total integral of the electric field, psi is basically the electric field fluctuation squared, is not going to change, and the energy associated with the wave is not going to change. The rest is history. From here on, it's just showing what I just told you. So now what I'm going to do is I'm going to go dive a little bit deep into the explanation of these two statements with the two invariants. So my psi, which is my electric field, is going to have an amplitude and a phase. And I'm going to do something else because there's a convention in the field that a lot of engineers use. They use the amplitude as an exponential of some function chi. So it's as if you wrote psi is exponential of chi plus I times s. That's the phase. The phase is real, and A is real. That means you cannot write A as some e to the I something. No, it's real, point, that's it. So now, my total phase is going to be S plus kz minus omega t, because I took a Fourier transform before. So, now, for those of you who have done optics, the astronomers should know this. The derivative of the phase gives you the wave number. Derivative in the direction of z gives you the wave number along z. The derivative perpendicular to z in the plane perpendicular to the direction of propagation gives you the wave number in that direction. And the derivative with respect to time is just minus the frequency. These are known because there's conservation of, if you take now the derivative, the divergence of this grad term S, which is the k vector, you get a curvature term. This is a curvature term. Remember second derivative? Or if you have a surface, the gradient constant along normal, the curvature tells you about. Remember that, but think of the equations for gravity, right? That people these days, people do GR, gravitational waves, right? How do you write the equation, Poisson's equation for the gravity field? It's grad squared of the gravity field equals to the mass. They say the mass tells space how to curve, and the curved space tells the mass where to go. Okay? So that's the curvature. So now the curvature is in the phase. So if I have a phase front, and it's curved, it's where the curvature happens that diffraction happens. If there is no curvature, there is no diffraction. If there is flat surface, no curvature, the second derivative is zero, I have only a refraction. So now I rewrite my wave equation. Now I have an equation for the amplitude, that's the equation for chi, that's the equation for the phase with respect to z, and I can identify now all of my physics. All of it is known now. This term is what causes refraction, this term is what causes diffraction, and in the phase I have a refraction term and a diffraction term that will give me the total electron content, because if I integrate with respect to the direction of propagation of the phase, you integrate the density, and that's the total electron content. So I have a way to access the total electron content. So, this is the refractive limit, refraction. In these equations, I only keep the refraction terms. So the phase is proportional to the total electron content, and then I could rewrite this equation using ray equations. Dx dz is rho per s over kl squared. So you can show that if you have refraction, the amplitude doesn't change. D chi is 0. So if I'm in the refractive limit, the amplitude of the wave should not change. Remember, the graphs that I had before, the data, for the amplitude, there's a shallow slope and then a steep slope. The part where it's shallow, the amplitude is not changing. All the frequencies have the same power. That's the refraction. That's the large scales. Large scales cause refraction. And on top of it, and in this case, the phase is just the total electron content. So I can calculate total electron content, which is a function of, n is a function of x and z. So this is a function of x. So I have a relationship. So if I have the mass of the total electron content, that means I have the mass of the phase. The diffraction limit. The diffraction limit, now I keep the curvature. Just keep the curvature. But now, if you look at the curvature of the amplitude along Z, that's proportional to the curvature. That means if I want to see change in the amplitude, I have to have curvature in the density. Curvature in the density means I have diffraction. The rest is just algebra. The rest now is algebra. I'm gonna go quickly through these because what I need to know is how to relate. By the way, how many use S4? S4 for scintillation. S4, the signals. Sigma, phi, and S4. You know, how do you know that for those who do scintillation calculations or scintillation analysis, that the first thing you do to know if there is scintillation according to the classical techniques is you calculate basically the variance in amplitude and the variance in phase, right? One is S4. This is S4. You can show that this magnitude is S4 and it depends on the tech. And I'm not going to say much more than that. Now I go back to my invariance. The invariant of the intensity, now I could write it in terms of the amplitude, and then I use Parseval's theorem. So Parseval's theorem tells me that this integral is the same as this one, same as this one. It's invariant. And then I'm going to do the same thing for t. So now I'm going to get the power laws. So in the refractive limit, refraction, I can show that if this is a power law, if AQ squared is Q to a certain power, that power becomes invariant, right? Because this doesn't change. I doesn't change. And T doesn't change as well because the Graph squared, we're in the refractive limit. There's no curvature in the phase. So I'm going to get the same power law for both I and T. That means in the refractive limit I should see only one power law. So I see flatland, one power law. So in other words, if I have this AQ, Q times AQ squared, if I start with a power law like this, the only way that the power law could change is if the area underneath remains invariant, because it's an integral over Z. So whatever power law I'm going to have, it can change from this power law to this power law as it propagates along Z. And I'm going to go in the diffractive limit. It's a little bit more complicated because I have the power law for the first invariant, and I'm going to have a completely different power law for the second invariant, because now the power law of the density is very important because I have small scales that are related to the diffraction limit. So I have a physical explanation for the two power laws, but it's not too convincing because I express the power laws in terms of integrals. So I'm going to move to statistical mechanics because it's a much more powerful technique. So I am going to define a probability distribution function for the amplitude component. So remember psi of q, the extra a Fourier transform in the direction, in the horizontal direction. So, and I have two invariants. I can show from statistical mechanics that the probability distribution, this probability distribution for my set of amplitude is 1 over the partition function times the exponential of a coefficient times IQ minus beta times TQ. This is, take it as a theorem in, for those of you who have done statistical mechanics, This is a canonical distribution. You know, there's micro-canonical, canonical, grand canonical. Micro-canonical, everything is open. No energy can be exchanged, particles can be exchanged. Canonical, the energy is conserved. So you need to constrain. So I have a probability distribution that goes up this side, where IQ is just Q times psi Q squared, TQ is this term, and you can show it from the equation. So it's not very complicated. It's a graduate student exercise. So I'm going to put these two functions in here, and then I'm going to calculate. So my probability distribution function is 1 over z times this exponential. So if I take an average, any average, the average of psi q squared, you know, this looks like a Gaussian, right? It's a Gaussian in this field, except that you're thinking as Gaussian with one single variable. This is a field. So if you took the average using p, so you do an integral of p times psi q squared d psi q, this is what you get. So you get psi q. So if you get psi q, you can go back and calculate iq and tq. So now I have two power laws, and these are the limits. And you can see the power laws appearing. You know, you get the q squared, and if you take a Taylor expansion of some sort, whether you have small scales or large scales, the moment you do that, you're going to get two power laws. And I'm going to go through the two power laws. Before I do that. So I have the limits. I know how my power spectrum is going to be, and I know what type of power laws I'm going to have, and I can compare them to the experimental quantity. Now, I'll do another trick. Another trick is to show that the average of Q, the average of your wave number where the most power is. You know, you have these power spectra, you have a maximum and a minimum, and you have noise, so you need to know how that average is going to change. So I'm going to calculate the variance, or the standard deviation. You can calculate it and then take the derivative with respect to z. So if you calculate it, you get it as a function of t over I, which are two invariants. So these don't change with z. Well, with the constant density, if I am in the refractive limit, the density doesn't change. Then the derivative of this with respect to z, this is 0, this is 0. So it gives me how q squared changes with z. And you can see if the variance, if you take a p, and as the p propagates, it becomes wider, ddz is positive, and because of this minus sign, ddz of q squared is negative. That means the power moves towards large scales. Right? So if I take ddz to be positive, this needs to be negative, which is equivalent to saying if the spectrum in I broadens, its average wave number must decrease. So as it propagates down, instead of going towards small scales, it goes towards large scales. So the power spectrum goes up. And that's exactly what we see experimentally. That's it. So the conclusions, two power laws are expected when small scale irregularities arise in the atmosphere. The small scale structures can cause diffraction and affect directly the amplitude. In the absence of small scale irregularities, one should expect a single power law spectrum that dictates refraction. The phase is affected, but not the amplitude. That means refractive events, you see an amplitude that doesn't change, but a phase changes. Diffractive events, the amplitude changes and the phase changes. And that's it.